Channel deals not with quantum things, but
yeah, but so you have your channel is not classical, but it's a quantum channel. And you want me to define? I mean,
okay. Yeah, no, just
it's not immediate to formulate all those things.
Okay, let's go on. So this is nice, but why is it actually classically hard? This promise, and actually this turned out to be harder than I thought, and we needed this theorem of Frankel and Reudel, which says that if you have, which is nice in its own right. So not in the least because it was a $250 problem of Erdős. It says the following: suppose you have a family of sets S and T that have size n over 2, subset of 1 of 2 n. And suppose that for all members of the family S in S and T in T, you have that the intersection size is not n over 4. So you have this.
The year is 1981, not 87.
Maybe in Russia it was
the
90.
same problem where the conjecture, both the conjecture was solved using this one. I
may have the date wrong, but I mean I did read the paper, so I think it was 87. But anyhow,
okay.
So it says that if the intersection of these two things is never n over 4, then actually the size of these two sets has to be relatively small. It cannot be everything. It cannot be 4. So if there was no restriction, it could be 4 to the n. And now it's 4 to the 0.96 times n. So it's significantly smaller.
It's a very strange problem. How on earth Erdős have come to such a problem?
You have to ask Erdős. That's not possible anymore.
The star is a product. S times T.
Harry,
yes.
For instance, if
the
n,
product of the cardinality.
n is not multiple of 4.
Yeah, you need that. Yeah, you need these things. Okay, and it's a strange problem. It's a strange thing, and the way we use it is the following: we say that if we have a protocol that solves equality prime in say n over 100 bits, then actually from this you can get a family S and a family T that satisfies this forbidden restriction thing, but that's larger than what they claim. So actually it's a very natural thing to have because it allows you to prove this law. Let me show you quickly why that's the case. So take the thing for granted and let me show the communication thing. Again, as usual, I interpret strings as a set. So x1 up to xn is the set x where I put the element I if xi is 1, and I will use only x's because remember in this equality prime I only had oh no, actually, no. I will only use x's which have exactly n over 2 ones. So I actually restrict the problem further. Not Alice and Bob not only have a promise that the Hamming distance is n over 2, they also know that they each have n over 2 ones. And note that the number that will not significantly reduce the number of strings because I still have n choose n over 2, which for the sake of the argument, I will just still call 2 to the n. I'm lying a little bit, but it's still large. And also note that this easy fact that if the Hamming distance for such strings is not n over 2, then that will mean that if I interpret the strings x and y as sets, that the intersection is not n over 4. On a piece of paper you can convince yourself that this is a true statement. So the Hamming distance is not n over 2 is equivalent to saying that if I interpret these guys as sets, the intersection size is not n over 4. Another notion that you probably know is that of a rectangle, if Alice and Bob have input x and y, and then if you look at the conversation that they have, and it's m, and if you also have that x prime and y prime yields that same conversation, then necessarily also x and y prime will give you conversation m, and x prime and y will give you conversation m. Or put differently, a protocol cannot, if a protocol doesn't distinguish between x, y and x prime and y prime, it will not distinguish these cases either. So imagine by contradiction that we have an n over 100-bit protocol for our equality prime problem. Now let's zoom in on the diagonal on the x1, x1, x2, x2, x2 to the n, x2 to the n pairs. And again, here 2 to the n is a little bit of a lie because I only had n over 2 bits. Forget it. And now let's look at all the conversations that could arise. There's only 2 to the n over 100. So by counting, there has to be a conversation that is used frequently. Namely, this many of these inputs, 2 to the n over 2 to the n of 100 of the inputs induce communication mk. There they are. I relabeled them x1 up to x2 to the 0.99n. Now notice that by property of a rectangle, by the property of communication protocols, if xi and xj induce the communication, then all the pairs xi, xj also will give communication mk, right? Because it has to be a rectangle. If the protocol doesn't distinguish between these guys, it also doesn't distinguish between all the subpairs. So in particular, since the protocol is correct, and since these strings of course are not equal, they have to fall inside of the promise, right? The protocol, it says, it will say 1 on these, it will still say 1 on these, so in particular they should fall outside of the promise. And so that means that if the Hamming distance between xi and xj is not n over 2, that means that the intersection of xi and xj is not n over 4. Right? Because protocol says 1, and hence it doesn't say 0, so it should be inputs that fall outside of the promise. So particularly if I now set s and t equal to x1 up to x2 to the 0.99n, then you see that you have the product of these two being larger than this, contradicting the Frankel-Rödel here. Okay, so I kept it in because I also think it's a nice connection with combinatorics and combinatorial statements. Other quantum algorithms. Oh, actually I have 3 more minutes, I guess, because so in general, if you have a quantum algorithm which will look something like this, you have a unitary query, etc. Then what I show to you is that somehow you can replace this query, if you do it smartly in the Deutsch-Joseph problem, at the expense of log n qubits communication. So in particular, if you have an algorithm, then if you slice it up correctly, you can use it as a communication complexity protocol, where instead of making this query, you have information going from Alice to Bob and from Bob to Alice back. And so if there's an algorithm, when we saw the Deutsch-Joseph algorithm with one query, then you can slice it up, and it gives you a one-round communication protocol. But you can do this in more generality. And for example, you can apply it to Grover's algorithm, where we have this OR of x1 up to xn, which had this quadratic speedup. And note that there's no promise here. That's nice. And well, you can sort of do the same trick, only now you don't use the parity, but you use the AND. And so Alice has x, Bob has y. And I want to solve the non-disjointness problem, or the disjointness problem, which is a well-known problem in communication complexity. So Alice and Bob have their strings, and they want to know whether they have a common index, whether they have an index where they have both at 1. And if you do the same trick as before, you can reduce this to some string z, where the z is the end now of the two inputs. And it's well known that you cannot compute this classically probabilistically with less than a linear number of bits. This is proven due to in '87 Kalyana, Sundaram and Schnittke, and also Razorov has a proof of this. Was that independent actually? No, it was just cleaning up the...
Actually, I looked at that over. It's also
yeah.
which can be simplified.
However, if you use this trick, the Grover's algorithm and the reduction, then you get a square root of n times log n qubit protocol, which has been improved by Ambarnis and Aronson to square root of n qubit. And also Sasha proved in '03 a very deep and interesting result, that the quantum communication complexity of disjoint is exactly square root of n. So this is tight. Well, this is another way of saying it. It's a pointed scheduling. There's many other functions, and this is a thriving field. For example, there's an exponential gap by Ramras for the two-way quantum communication complexity and bounded error. It's still open, I should say, whether there is a total function for which the quantum communication complexity can be exponentially better than the classical bounded error.
Say it again.
So Ramras has a function which has a promise function again, where classically you need a polynomial number of bits.
So the challenge is to remove the promise.
Yes, this is open still. Let's see. Okay, maybe I should stop here.
As you wish.
What do you want? Shall I stop? Or I can go on for. Let me quickly say.